Okay, so what we've been looking at is the logical foundations of Prolog, and in the last class, all we had seen is first order logic, right? And we saw various properties of first order logic, and in particular, we saw that the question of validity in first order logic is not decidable. And we said, can we do better, right? Can we do better by um, restricting the language somehow so that the resultant language is semi-decidable, right? So that's where we wanted to get to. And in this lecture, what we will do is we will see what that restriction looks like, why that is semi-decidable, and where Prolog comes from, right? So that's the rest of the lecture today. Um, so yeah, so what is semi-decidability, right? So the definition is that if I had a language, L is said to be desirable if you can build a Turing machine that accepts every string in L and then rejects every string not in L, right? So this is an algorithm that can um, either accept or reject every string that is in L. And if you can build such a Turing machine, then that language is said to be desirable, right? So what is semi-desirable now? Semi-desirability is um, if the language is if you can consider the language L and assume that you have a Turing machine, right, which given any string that is in L accepts that string in L, right? But for every string not in L, it either rejects it or it may loop forever, right? So this is where semi-desirability comes in, right? So if you have a desirable language, you can the Turing machine will always reject every string not in L. But here, if you give a string to this Turing machine, which is not in L, then it rejects it or loops forever. And this is the high-level definition. Um, and Prolog is Prolog is a program which is it's a language and an interpreter which has this property of semi-desirability. Okay, so in order to look at Prolog, what we are going to do is to take first order logic and restrict it. And in particular, what we are going to do is to define this subset of first order logic called definite logic programs. Definite clauses. So definite logic programs are constructed out of definite clauses. These are just formulas, right? But they have a certain restriction. And definite clauses are such a restriction that make the first order logic, the subset of first order logic, semi-decidable, right? And Prolog is essentially programming with definite clauses. Prolog, although there is a language, the concept of logic programming in the style of Prolog is essentially programming with definite clauses. We will see how this comes through. So I should, before I go on, I should define what definite clauses are formally, right? So that we can have the foundations for reasoning about what the restriction is. Okay, so first off, we start with clauses, right? A clause is an atomic formula, right? In first order logic itself, right? When we say an atomic formula is some formula that does not have any connectives at all. For example, we've been looking at this running example of natural numbers. An atomic formula in the running example is even of x and prime of x, but not negation of even of x or even of x or prime of x. All of these include connectives, so they are not atomic formula. The only atomic formula here are even of x and prime of x, right? Okay, that's atomic formula. Now, what is a clause? A clause is a first order logic formula, okay, which has a specific structure. The only structure that is allowed is you have an outer for all, right? You should have for all only on the outside, and you have a series of disjunctions of L1, L2, L3 up to Ln, where every Li is either an atomic formula, right? Like this one, even or prime, or the negation of an atomic formula. So you could have not even, not prime, and so on. So that's the only structure that is allowed. Observe that this is a restriction of the formula that you can construct, right? We restrict such that the for all quantifier appears on the the outside. We don't have any existential literal in this construction, and the only connector that is allowed is um, disjunction of L1s, where each L1 is either a positive literal, an atomic formula, or a negative literal, a negation of an atomic formula. Okay, so these are known as clauses. So each one of these is known as a clause. So that is a clause. We are going to define a subset of clauses, okay, which are known as definite clauses. A definite clause is a clause that has exactly one positive literal. So again, recall that positive literal is an atomic formula, negative literal is a negation of an atomic formula, right? So a definite clause is a clause that has exactly one positive literal. So there is one positive literal here, and everything else is a negative literal. And you have for all quantifier on the outside. So when you have this, right, we've looked at logical equivalences earlier in in yesterday's class. When you have not P or Q, that is equivalent to P implies Q. So you can rewrite this whole formula as, I'm dropping the for all quantifier here, but that's implicit here. You can write this as A1, because we are going to extract this negation out, right? Using the logical equivalence, all of this becomes conjunctions. So what you have is A0 is implied by the conjunction of A1 to AN, where n is greater than or equal to 0. It might be 0, but it might also be greater than or 0. And simply in Prolog in logic programs, because conjunction is sort of the only operator that can appear there, we just use commas. So every definite clause we write as A0 implied by A1, A2, A3, up to AN, where n is greater than or equal to 0. Observe that this is sort of getting close to what we had seen in the Prolog running example in the Prolog basics lecture, where we defined the ancestor relationship and so on, right? So we are getting somewhere here. Essentially, Prolog is nothing but a finite set of definite clauses, right? The set is finite, and each one is a definite clause, and that is a Prolog program, right? So here is the actual relationship between definite clauses and Prolog, right? There are two forms of clauses that we saw in Prolog, right? We had facts, right, and we had rules, and both can be written down as definite clauses. Whenever we write a fact such as 0 is even, right? Even z is a fact, because that's the base case of the recursion. So we say 0 is even. This is a fact that you can load into the Prolog interpreter, right? And the equivalent definite clause is you have a for all quantifier on the outside on some variable, right? Some free variable that does not occur on the right hand side. It's just for satisfying the structural property, right? For all x, where x is not used here, right? Even of z is implied by true. This T stands for true. So this is only there because definite clauses allow n to be greater than or equal to 0. N is equal to 0 here. So we simply replace that by true, right? So for all x, true implies even of z, right? That just means that even of z. And we've written it in the form of a definite clause, okay? So that's how Prolog facts can be rewritten into a definite clause. And the next one is Prolog rules. It is a bit more natural, right? We had a rule which said x is an ancestor of y if x is a parent of z, some z, and z is an ancestor of y, right? So you can write this into a definite clause where you have all the variables on the outside, right? Universally quantified. So we have for all x, y, z, ancestor of xy is implied by parent of xz and ancestor of zy, right? So we're just rewriting the rule directly into a definite clause. And because of the logical equivalence between implication and there exists, right? So if you push for all existential variable into an implication on the left hand side, that becomes an existential variable. So all I've done here is I push the z variable, which is on the outside. It's outside this entire formula here, entire term here. I'm pushing z to the left-hand side of an implication, right? We write implications in the reverse direction, so left-hand side is here. When you push z inside an implication, it becomes that there exists, right? And this is much more natural to read. This is the logical reading. This is what we say in English when we look at this particular rule in Prolog, right? We say for all x comma y, x is an ancestor of y if there exists a z such that x is a parent of z and z is an ancestor of y. So this particular rule in Prolog exactly corresponds to this definite clause. So when we describe a Prolog program, all we are doing is we are just describing a set of definite clauses. Okay, so that's the restriction of first order logic that Prolog is. Just moving on, right? So we've chosen to restrict first order logic in a very specific form, right? Actually, what does this bias, right? If you sort of take a language and then restrict it, the point of restriction should be it gives us some property that is not given by the larger language, right? So what property do we get from going from, say, first order logic, full first order logic, which we know is undesirable, right? And we sort of restrict it to definite clause program. We have this very nice property now, which is that every definite clause program has a model. If you write down a set of definite clauses, you always have a model for that definite clause program. Essentially, what this means is that a model for a first order logic formula is equivalent to a satisfying assignment for a propositional logic formula, right? So what this says is if you write down a set of facts and rules in a Prolog program, you can always answer queries on the program, right? Because it has a model. And you can also read this as every definite clause program is consistent. You cannot write an inconsistent definite clause program. This is very important, right? You cannot write something that is inconsistent, such as this one. So I cannot write a definite clause program that is f and the negation of f. This is invalid, right? This is not a valid statement because there is no, you cannot satisfy this ever, right? So why is this case, right? Why is it the fact that every definite clause program has a model? This is just an intuition, right? This is not a full proof. This is just the proof sketch. The intuition is that in a definite clause program, you cannot encode negative information. This is the key bit. You cannot encode something is not true at all in a definite clause program. This is true with Prolog as well. We will study negation, a restricted form of negation later. That is quite weird. It works in certain cases, but it behaves very weirdly. But you cannot encode facts such as 1 is not an even number. All you can say is 0 is an even number, 2 is an even number. You can say 1 is an odd number, but you cannot say 1 is not an even number. Or you cannot say if x is an even number, then x is not an odd number. This is, I'm just going to give you this intuition. You can think of why that is not possible because of the structure of the restriction. I will leave it to you. But it's important to take away this intuition that you cannot encode negative information because you cannot put negation at arbitrary places. For example, this is not a definite clause because we have a conjunction here, right? In a definite clause, everything is a disjunction. I will let you work it out in your own time, but the important bit is there is no way to encode negative information. Okay, so so you can ask, right? So every logic program written using definite clauses has a model. So what does this help us? So you can ask, okay, how do we construct this model? But the important question that you should ask is, why should we construct this model, right? Why should we compute the model, the satisfying assignment for a definite clause program, which is a logic program? Again, the intuition is that, as I mentioned, models for a first order logic program is the same as, it's analogous to satisfying assignments for propositional logic programs, right? So here we are working with definite clause programs. So we also saw that every definite clause program has a model, which means that we can always find a satisfying assignment for a logic program. Right? So why is this important? So consider this particular program, right? This is a subset of the rules and facts that I had in the motivating examples in the first lecture, where we defined the Game of Thrones family tree, right? So I'm having a single fact here which says Ned is the father of Rob, and then I have rules, a couple of rules which defines parent and ancestor relationship. So what does it mean to have a model for this particular set of Prolog clauses? When we say we have a model, essentially you can build a database of facts, right? This database will contain everything that is true about this program. And that is essentially the satisfying assignment for this program. And what are the queries that we are asking? All the queries that we are asking is, can you find something that is true for the model of this program, right? Oh, you have this program. I said in the first class, I said the logical model of Prolog program is build a database. Because every definite clause program has a model, we can build a database for every Prolog program. And all we are doing in a query is looking up facts in the database, right? What are all the assignments that we can give to X here in this query that are true in the model of this logic program, right? So the fact that we have models is what is allowing us to answer queries in a Prolog program. Okay, so that's the key intuition that I want you to take from this logical foundations lecture. So the next question that we want to ask is, okay, that's fine, but you also told us that we are not going to compute a database of facts, right? We are not going to compute all the possible assignments for all the possible ground terms, right? All the possible satisfying things for ancestors such that it does not include a variable. We're not exactly going to build a database and then look up facts in the database, right? That's not the computation model. So the next question that you want to have is like, how do we actually compute the models for definite clause program? Because that is intimately related to answering queries about Prolog programs. Okay? But in order to look at that, we will have to see more definitions. So what I will do is, like, if you have any questions on any of this, I mean, these are mostly definitions so far. You can ask, because I'm going to throw more definitions at you, unfortunately. But if you have any questions at this point, you can ask. So sort of this pause is also important because I'm going to throw more definitions, and I don't know about you, my mind cannot take definition after definition all the time. So this is just a pause so that you can also like take in what was said and then be ready for more definitions. Okay, the pause was useful anyway. So the last thing that we are going to see, right, is how does Prolog computation actually work? The rephrasing that question is essentially, how do we compute models of definite clause programs? Okay. So more definitions. So these are definitions that are specific to logic programs, right? So the first definition is the definition of something called a Herbrand universe, right? So it says that given a logic program P, when I mention logic program, think about definite clause programs, right? I use these terms interchangeably. They are whenever I mention logic program, I mean definite clause program. So when you are given this logic program P, we can define a thing called Herbrand universe of the program, logic program, which we write down as UP, U of P, which is the set of all ground terms that can be formed with constants and functions, symbols in P. So ignore the predicates, but this is the set of all ground terms that you can form with just the constant and functions, right? So what is a concrete example? In our encoding of natural numbers, we had a single constant. We had a single constant z, and then we had a function which is s of x, right? And the Herbrand universe for this particular logic program is z, sz, sszz, ssszz, and so on. So this is just a set of all terms that you can, ground terms that you can construct with the constant and the function symbols. Again, I should define what a ground term is. So a ground term is one which does not have any variables. Okay, so we have s of x here where x is a variable and there are no variables here. So everything is a constant or a function with a term which is also recursively either a function or a constant. There appears no variables here, right? Okay, so that's Herbrand universe. So if there are no function symbols at all, right? Imagine we did not have s of x here. Then by definition, our Herbrand universe will be finite, right? You can only have constants. And then we cannot construct more and more ground terms such as these ones. So if there are no function symbols, then the Herbrand universe is finite. And if there are no constants in the logic program, it is possible that there are no constants in the logic program. We add an arbitrary constant just to build up a Herbrand universe. So this is like an edge case. We won't ever encounter this case in practice, but if there are no constants, then we simply add an arbitrary constant to the Herbrand universe. Okay. So we looked at constants and functions. Now we have clauses and predicates, right? So for that, we define something called a Herbrand base. The Herbrand base of a logic program is denoted by B of P, is the set of all ground goals that can be formed with predicates in P. So a goal is something that is a fact, right? And if you look at an example, it will be clear. So for our encoding of natural numbers, so the constants that we had are z and s of x. Let's assume that the only predicate that we have for now we are considering is even of x, right? Let's only consider that as the predicate. If that is the only predicate, and given that we have the constant z and the function s of z, the Herbrand base of this logic program will contain even of z, even of s of z, even of s of z, and so on. So this is all the things that you can construct using the predicates, right? The clauses and the constants and functions. And the observation here is if the Herbrand base is infinite, if you have functions where you can construct arbitrary terms such that your Herbrand, sorry, this should be, so Herbrand base is infinite if your Herbrand universe is, right? If you can construct an infinite Herbrand universe, then your base will also be infinite, right? So because we have z, s of z, s of s of z, s of s of s of z, and so on, my Herbrand base, it simply wraps even around these terms, will also be infinite. So the idea is that if Herbrand universe is infinite, then Herbrand base is also infinite. On the flip side, if Herbrand universe is finite, then Herbrand base is also finite. Right? So this is just the nature of how functions behave. Okay, so we looked at two definitions. We've looked at Herbrand universe and Herbrand base. We are going to look at Herbrand interpretation. And Herbrand interpretation is just a subset of Herbrand base, right? This is easy. So you take an interpretation. What is an interpretation? You take the Herbrand base, take a subset. Any subset is an interpretation, right? Why is this useful? An interpretation is assigns true or false values to elements of the Herbrand base, right? So when I pick something which says even z drops the even of s of z, but only has even of s of z, implicitly that particular interpretation is saying that even of z is true, even of s of z is true, even of s of z is true, and so on. That's the idea of having a Herbrand interpretation. And finally, we come to the definition of a Herbrand model. Again, what we are slowly moving towards is actually finding out um, what is the meaning of a program that you describe in Prolog, right? And that model is an interpretation, right? A model is an interpretation, just like what we saw in first order logic, such that for all ground instantiations of the form, so we have rules in logic programs, right? Definite clause programs. So whenever you have a rule like this, if B1, B2, B3, B4 up to Bn belongs to the model, right? Then A also belongs to the model, right? So this is basically saying if you have B1, B2, B3 up to Bn in a model, then A also belongs to the model. So how does this work? So let the logic program be even of z, right? I'm saying 0 is even, and then s of x is even, right? X plus 2 is even if x is even, right? So what is this definition saying? If b1 to bn belongs to m, right? Here we have true. As we saw earlier, you can read this as for all x, even of z is implied by true, right? True always belongs to the model. So true is just true, right? So even of z belongs to the model. If even of z belongs to the model, then even of s of z belongs to the model, right? So Herbrand model of this program includes even of z, even of s of z, and because even of s of z belongs to the model, even of s of z belongs to the model, right? So that is sort of telling you how to construct all the things that hold true for a logic program. Okay. But mathematicians are quite weird. I don't know why they use this particular form of encoding. So this is Herbrand model, right? But surprisingly, Herbrand model also includes may include elements from S, where S is even of 1, even of 3, and so on. This is quite weird. This is just how mathematicians choose to describe sets, right? When mathematicians describe this definition, this is a mathematical definition, they say what should belong to the model, right? They don't say what shouldn't belong to the model. And the problem is that if you don't describe what shouldn't belong to the model, you can have arbitrary elements that belongs to the model, right? So you can observe, if you closely read this definition, it only says that if B1, B2, Bn belongs to the model, it's a set, right? I'm describing a set. I'm saying, oh, what are the elements in the set? If you have one of these ground instantiated B1 to Bn, all of these B1 to Bn belong to the model, then A also belongs to the model. Concretely reading this, if even of Z belongs to the model, then even of S of Z belongs to the model. It doesn't rule out what doesn't belong to the model, right? So we are sort of describing sets by what should be in the set. We are not describing what shouldn't be in the set. So this is the difficulty. So when you have a Herbrand model, that particular definition that we saw in the previous slide does not preclude elements such as even of 1 and even of 3 from belonging to the model. This is just a quirk of how we do mathematics, right? Mathematicians should really use constructive definitions. So the way we write programs, right? We sort of look at a program, we start with the ground terms, base cases, and then inductively build it up. Mathematicians tend to not use it. Unfortunately, this means that Herbrand base of a definite program is always a Herbrand model, right? Herbrand base is this anything that you can construct, right? In this particular program, Herbrand base contains even of 0, even of 1, even of 2, even of 3, even of 4, up to even of infinity, right? That is also a model because by this definition, anything can belong to the model, right? And yeah, so this is not at all useful, right? This particular definition seemed to be going in the right direction by looking at the rules, but because of this non-constructive definition, it's sort of looking at what is in the set and does not describe what is not in the set. We have to have one last definition. Finally, we are going to define the least Herbrand model, right? So this is mathematicians' way of getting back to what is what is the smallest set, what is the smallest model that you can build, and they have this curious way of describing it, which is that a least Herbrand model is one which is the intersection of every Herbrand model, right? So there are some rules about what should belong to the set. There can be arbitrary things that can also be added to the set, right? But if you take all of these Herbrand models where arbitrary things can be present according to the rules, right? And if you take an intersection of all these sets, the set that you will have is the smallest one, right? Of all of these models, and we call this least Herbrand model. So we define a least Herbrand model as the intersection of every Herbrand model. So we throw away all these nonsensical things out of the Herbrand model, and we get the least Herbrand model. And we have the definition that we want for precisely describing a meaning of a logic program, right? So, so now what we've defined is we precisely have defined this least Herbrand model, which is a set, right? Which is a set which contains one entry each for every fact that holds true, right? But nothing else. So if you don't have a particular fact that is in a least Herbrand model, then if you ask the Prolog program, like query the Prolog program whether this is true, it will come back with false, right? And that's the notion of building a least Herbrand model. And okay, so we've seen a lot of definitions. So let's try to refresh our understanding of these definitions, right? So let's take this languages, right, with constants Rob, Rickard, and Ned, right? And we'll consider two predicates: father, a function symbol with arity 2, and ancestor with arity 2. And we have the facts, which are Rickard is the father of Ned, and Ned is the father of Rob. And we have the rules: X is an ancestor of Y if X is a father of Y, and X is an ancestor of Y if X is a father of some Z, right? I'm not going to tell you what Z this is, but Z is the ancestor of Y. So this is the same as what we had seen earlier. So given this languages, these constants, these predicates, which of the following statements are true, right? So, so the first question is the Herbrand universe U of S infinite? Recall that a Herbrand universe for a language is infinite if you have function symbols. Do we have function symbols here? We don't have function symbols, right? We have the constants and we have predicates. We don't have function symbols, right? So this is false, right? Is the Herbrand base finite? Is the question. Recall that Herbrand base is finite if the Herbrand universe is finite. So is the Herbrand base finite? Yeah, it is finite. That's right. So okay, so now we know that the Herbrand universe is finite and the Herbrand base is finite. The next question is, does the ground term father of ancestor of Rob belong to the Herbrand base of S? So does this term belong to the Herbrand base? So base is the set of all things that you can construct with the predicates and the constants and the function symbols. So does this term belong to the base? So yeah, the answer is no, right? Because the problem is that we are syntactically wrong here. Father is a predicate that has arity2, and ancestor is also arity2. So it takes two arguments, right? That's right. We are applying to one argument. I mean, this is ill-formed by construction, so it does not belong to the Herbrand base. Okay, and so the fourth statement says that there exists some model M such that father net belongs to M, where M is the Herbrand model of the program. Is this true? Recall that we have two definitions, right? We have least Herbrand model and Herbrand model. What I'm asking is whether father net is the father of net belongs to some M, where M is the Herbrand model. Is it true or false? It's true, right? Herbrand model can have nonsensical things. It describes what should be present. It doesn't describe what shouldn't be present. And as we saw earlier, the Herbrand base is also a Herbrand model. This is a well-formed statement, right? Whether this is true or false is like beside the question. I can write down. I mean, this father has this father predicate has arity2, and these are valid constants from the language. This is part of the Herbrand base, and hence this is part of the Herbrand model. The last one is actually asking the useful question, right? Is father net um, does father net belong to M, where M is the least Herbrand model? No, right? So that's the idea there. So the least Herbrand model is meant to be capture the precise meaning of what the program conveys. You can even answer it intuitively, right? If it is a precise meaning, then according to these rules and facts, this is not true. So, but you can also assume that you can go from the definitions, right? Least is the intersection of every Herbrand model, and the smallest model does not contain father net. Okay, that's good. So it seems like we've managed to understand this reasonably well. And these are important, right? It's important to know where these things come from, so that if you happen to be in a position later where you look at a particular problem and you're like, okay, this looks like a logic programming problem. How do I think about this problem? These sort of terms will come in handy. So that's the idea of teaching all of this. But anyway, so it looks like we've gotten some of the ideas from this from the part of this lecture. Yeah, this is precisely what I had explained earlier. So okay, so we've sort of, we know how to define least Herbrand models, right? And the mathematical definition that we saw said, okay, compute all the models and then take the intersection of all of these models. That will be the least Herbrand model. Of course, we don't want to compute answers for our Prolog queries by enumerating all the models and then taking an intersection. That would just be impossible to do if you have function symbols, right? Because the Herbrand universe will be infinite. That procedure will not even terminate. So the question is, okay, all of this is fine. The definitions are fine. How do we actually answer the Prolog queries, right? How does Prolog compute answers to queries? So the interesting thing with Prolog is, in order to understand how Prolog programs, what Prolog programs do, you need to understand how Prolog works, right? Okay, so this is sort of a curious thing about Prolog. So Prolog is a very small language. In order to understand OCaml, right, you did not have to understand how the compiler works or how the garbage collector works or anything. So we had a nice model on top. We said, okay, we will work with this simple model, and we had models which are far removed from how you will implement OCaml, right? But for Prolog, this is, I mean, putting my programming language hat on, this is not the way I would actually implement Prolog if I were to do it again. But in order to understand how Prolog programs, what Prolog programs do, you need to understand how Prolog works underneath, right? It's like this weird thing where the the semantics of the program is fully described by only by the interpreter, right? So you need to understand how to implement a Prolog interpreter in order to understand how Prolog's programs work. This is quite curious. So I found it really interesting that the behavior of some program is so closely tied to the implementation, right? Um, so what really helped me was to actually go ahead and implement an interpreter for Prolog, um, and that is what you will do in assignment 7. So this is just a thing to say. In the last assignment in this course, what you will do is you will implement a Prolog interpreter in OCaml. So that's sort of mixing two ideas that we have studied in this course. So you'll take all of your OCaml knowledge, right, and use it to build an interpreter for Prolog. You will only build the interesting bits. You won't have to implement the parser and everything. Just like how we did for lambda calculus, you will go ahead and implement like a full Prolog interpreter. It's not a large program, but as you'll see in the rest of the course, right, there are some subtleties which you can only understand by understanding how the Prolog interpreter works. This, look at the rest of the lecture as sort of a prequel for them, right? We'll come back to these ideas over and over again throughout the course, because in order to understand how Prolog programs work, you have to understand the interpreter. But here is like a 10-minute intro to how Prolog works. So the core of how Prolog works is this algorithm known as SLD resolution, right? SLD stands for selective linear resolution with definite losses. Yeah, I don't know why people choose complicated terms. You sort of take a definite loss program, and then you sort of apply a particular procedure in order to answer queries. Importantly, right, this particular resolution algorithm, SLD resolution, is semi-decidable, right? What does that mean? If you ask for an unsatisfiable set of formula, it is guaranteed to derive false, right? It goes through the program and it guarantees that the program will terminate. This procedure will terminate. If you give it a satisfiable set, right, of formulas, so you sort of give it a bunch of rules and facts, and then you provide the query. If the query is satisfiable, then it may never terminate, right? So this is where the semi-decidability comes in, and this is also why Prolog has non-termination. It's Turing complete, right? Prolog itself is Turing complete. So we'll see what this SLD resolution is. I think the scariest thing about this SLD resolution is its name, selective linear resolution with definite losses. The actual procedure is actually quite natural and simple and intuitive. We'll go through what that is. So again, it is best to study this using an example. We have the same running example as what we had in the last class. We have a bunch of facts described, right, which describes the father relationship between Game of Thrones characters. We have the parent relationship, a parent of X, X is a parent of Y if X is a father of Y, and then we have the ancestor relationships. We have two rules for ancestors, right? Direct ancestor, who is a parent, and then ancestor with multiple hops, right? And then given these Prolog facts and rules, I'm going to try to answer the query, is Rickard the ancestor of Rob? That's what I'm going to try to answer. I'm going to try to apply SLD resolution from first principles, right? And I'm going to try to convince you that this is a reasonable thing to do. Okay, so the query is, so what is the query? the query says, okay, Rickard is the ancestor of Rob. The thing that you don't want to do is to compute the least Herbrand model for this program. Although you can do this for this particular program, if you have function symbols, then this program becomes um, the, 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 the procedure to compute the universe and the base becomes infinite, right? So you don't want to do that. But all you're asking is whether this particular ground term, right, Rickard is an ancestor of Rob, belongs to the least Herbrand model, right? So what I'm asking is ancestor of Rickard Rob belong to the least Herbrand model of P, the program? So how can I derive this, right? If you sort of go back to the definition of models, so it says what should belong to the model, right? It looked at rule and said if you have some rule, then that particular um, ground instantiation of that rule should belong to the model. We are going to apply the same intuition here, right? I see ancestor Rickard Rob, right? That's the query. So we use the term goals for queries because as you try to answer the queries, you will have more and more goals that you will have to answer. So query is the top level thing that you feed into the program, and internally the query becomes a goal, and Prolog might have more and more goals as it does the SLT's resolution. So I might use the term goals as well, but think about goals as just things that Prolog needs to show are satisfiable, right? So the first goal is it needs to show that Rickard is the ancestor of Rob. How can I derive this? Is what Prolog is going to ask. It looks at this rule, right? SLD resolution looks at the rules that can be unified from top to bottom. So these are father, 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 parent, parent, and it's looking at something that satisfies ancestor, right? And the first thing that satisfies, unifies with the ancestor is this particular rule. So ancestor XY unifies with ancestor Rickard Rob, right? Okay, that unifies. So I can get ancestor Rickard Rob if I can show that Rickard is the parent of Rob. Rickard is the parent of Rob, right? So that's the way Prolog SLD resolution works. And the logical view of that particular rule is for all xy, ancestor xy implies parent xy. We saw a few logical inference rules earlier in the lecture. You can actually apply those inference rules to convince yourself why this is a valid thing to do, going from this goal to this goal, right? But the intuition is this, right? If I want to show that Rickard is the ancestor of Rob, and I observe that there is a rule which says that ancestor of X is an ancestor of Y if parent of X is a parent of Y, then I can derive ancestor of Rickard Rob by showing that parent Rickard Rob is what Prolog is trying to do. So what it's going to do is to take this rule, and logically what it's going to do is to this holds for all xy, but I'm going to do for all elimination and pick x equals Rickard and y equals Rob, right? Substitute x equals Rickard and y equals Rob, and then apply the rule for implication elimination. So eliminate the implication. So we know that the goal is true because that is what I'm going to try to show. And we know that this holds true as well. Ancestor Rickard Rob is implied by parent Rickard Rob. If this needs to hold, then I need to show that parent Rickard Rob holds, right? So we started with the original goal, which is ancestor Rickard Rob. In order to show that this actually holds, our goal has now become parent Rickard Rob, right? So the original goal to derive ancestor Rickard Rob has been replaced by the goal to derive parent Rickard Rob. So Prolog tries to keep going down this route, right? It says, okay, can I show that Rickard is a parent of Rob? So how can you derive Rickard is a parent of Rob? Again, it goes through the rules and facts in the order in which they are described in order to see which one unifies. Father doesn't unify. Oh, I see parent XY, right? Oh, this looks like a nice term. Let me try to unify the term parent Rickard Rob with parent XY. and then I'm going to try to show that father xy holds, right? So it's going to go down the route, apply the rules. So parent Rickard Rob unifies with this parent xy, and then the goal now becomes father xy, which is specialized, becomes father Rickard Rob, right? So the new goal is now father Rickard Rob. So Prolog says, okay, I need to show that Rickard is the father of Rob. Again, it goes through the same procedure. It goes through the goals and facts in the order. Father unifies here, but the term doesn't unify, right? Rickard Rob is not a pair here, right? We have Rickard Ned, Brandon, Ned Rob, but no father Rickard Rob. So obviously, it goes through all of these father, goes through all the way to the end, and then finds that there is no term that unifies with our current goal. The current goal is father Rickard Rob. There is nothing that unifies. And then Prolog says, okay, SLD resolution says, this is, I cannot satisfy this goal. So what do I do? The important observation is when SLD resolution looked for the unifying term for ancestor, there were two terms, right? There is one here and there is another here. And we picked the first one. We went down the first path. We sort of hit a dead end, right? We went down ancestor. We went down this, sorry. We went down this rule. Oops. Let me try again. We went down this rule and then we came here and then we got stuck at father xy, right? But there is a second path as well. We could have chosen this rule. SLD resolution chooses the rules to apply in the order in which they are described. So now it goes back, right? We are stuck here. It goes back to this position and then says, okay, there is another option which I haven't tried. Let me try that option right now. So it goes ahead and yeah, okay, I should be here. So how can I derive? It asks the same question, right? How can I derive ancestor Rickard Rob? The first path led to a dead end. Let me try the second path. The second path was this term unifies with this term. But in order to satisfy ancestor xy, I need to have two goals now. So I have the goal to show that x is a parent of z, where x is Rickard. There exists some z, right? And z is the ancestor of y. So I need to show that both of these hold, right? I can derive both of these. Then I can show that I can derive ancestor Rickard Rob. So you can apply logical equivalences, you can apply these rules. But the idea is that you end up with two goals, where you say, I need to show that Rickard is a parent of some z, and z is the ancestor of Rob. Okay, where z is the same variable. So we use the same z here. So we have two goals, and SLD resolution picks the first goal, left-hand side goal, in order to do this traversal. So the current goal is now parent Rickard z, right? You can keep applying the same procedure. It goes to father Rickard z, and father Rickard z unifies with father Rickard Ned, right? So that unifies with father Rickard Ned. And Prolog says, okay, I found a satisfying assignment for this z. So it specializes that z to Ned in all of the goals that you have. So we have one other goal that is sitting on the side, right? So it says, okay, the first goal is satisfied. The second goal is now specialized to proving that Ned is the ancestor of Rob. Again, you can keep applying the same procedure. Ancestor Ned Rob can be shown by parent of Ned Rob, which can be shown by father of Ned Rob, right? You can keep applying this procedure over and over again. And eventually, this is also satisfied. And yeah, and hence we have proved that since both of the goals are satisfied, the goal one is satisfied and the goal two is satisfied, the original goal is satisfied, and hence proved. So what is proved? That particular question, whether ancestor of Rickard Rob is true, is satisfied by SLD resolution. So this is exactly how Prolog works. Okay, so what we've shown is ancestor Rickard Rob for the given program P is part of the least Herbrand model of P. So we've sort of applied the rule in this procedure, and this procedure is called SLD resolution. This is quite intuitive, right? And yeah, okay. So we will look at how, yeah, the I'll come back to this in the next class. I think there are only 2 slides more, but that's the idea, right? So you started with some goal and you apply this SLD resolution principle, which was actually quite intuitive. And then you computed the answer to the query. And in the last class, we'll complete this lecture and we'll go into more Prolog programming. I'll stop here. I've taken much more time, but I wanted to finish this anyway. We can reserve questions for the next class. Thanks very much.